In this last section, we want to cover what the basic concept of a limit is. And we want to look at it from all four representations that we talked about with functions: graphical, numerical, analytical, and verbal. So the first thing you see here in bold is the verbal description of what a limit is. We will use the notation, and this is read: the limit as x approaches c, f of x is equal to L. So the limit as x approaches c, f of x is equal to L. What that is saying, as this x value gets very, very close to c, so I'm going to keep getting closer and closer, but I'm never going to reach c, the y values get very, very close to L. So when we look at the L piece of the limit, we are looking at an output, or the y value. So the concept here is we are getting really, really close to this point of interest, which we call the c value. And when we get really, really close to the c value, what happens on the y-axis, or the output? It gets very, very close to this idea of L. So when we do this, we're going to look at limits from a couple of perspectives. The first is what happens on the left-hand side of c. The second is what happens on the right hand of c. And then the final thing is, do the two things meet up? Do the two concepts meet up, the left and the right-hand side? So let's start with the left-hand limit. If I have a graph, and let's say my graph here is the point 1, 2. I've got a straight line coming out there, and I've got a curved line going down there. The first thing is, if I want to look at a limit from the left-hand side, the notation will look like this. I want to know the limit as x approaches 1, and this minus sign, that's an exponent area, right? That's minus sign. That indicates from the left, or from the negative side of the number line. So the limit as x approaches 1 from the left, my function equals what value? So as I get closer and closer to x is equal to 1 on the left-hand side, what does my y get very close to? And you can see that it gets really, really close to 2. If I were to go to 0.99999, how close do I get to 1? And you can see that the value is equal to 2. The right-hand limit is a very similar concept, but going from another perspective. So let's say I've got this sine type of graph coming out from the right, and I want to know what happens as we approach 1 from the right this time. And this is not a continuous function. We see it then as just a straight line to the left. And this once again is going to be 2, 1. So the limit as x approaches 1, now I put a plus sign in that superscript area, or the exponent area. The limit as x approaches 1 from the right, the function is equal to 2. As I get very, very close from the right-hand side, so 1.00001, what y value am I very close to? And I'm very close to the value 2. The final idea is a two-sided limit. Let me go with the same ordered pair of 1 and 2. And let's say my graph looks like this. Now if I want to find the limit as x approaches 1, f of x is going to be equal to 2. When I don't have a minus or a plus in that exponent area of my limit notation, I have to look at what happens from the left-hand side as well as the right-hand side. So coming from the left, if I were to be at 0.9999999, I'm very close to 2. If I come from the right and I say 1.0000001, I'm very close to 2. So it's very important to realize that the limit value does not depend on the existence of the function at x is equal to c. So I could have an undefined point. What I want to know is what happens as I get very, very, very close to c, not right at c. So let's look at this example here. let's say I've got a function that looks like this. I've got the point filled in at 0, -2. And I want to know the limit as x approaches 0 of the function f of x. And notice how this one is the limit as x approaches 0. I need to look at the left-hand side and the right-hand side. So the first part I look at is the limit as x approaches 0 from the left. What does it equal? Well, as I get closer and closer to 0 on the left-hand side, so let's say I go -0.00001, what value do I get really close to? And the answer is I get very close to a +1. If I were to be at the point -0.0001, I'm going to be very close to 1. I'm going to be like a 1.0001, just slightly up. I then look at the limit as x approaches 0 from the right. And as I go from the right, you can see that it equals 1 as well. So then the limit of the whole thing is going to equal 1. We've got to make sure both of these things work. The second one here, the limit as x approaches 1 of g of x. Let's put g of x as being right here, and then right there. So once again, I need to compare my left-hand limit and my right-hand limit. So the first one, the limit as x approaches 1 from the left of g of x. As I get closer and closer to my point of interest from the left-hand side, I can see my output is 1, or the y value is 1. The limit as x approaches 1 from the right, g of x, as I get closer and closer from the right-hand side, you can see that my y value is 3. That's a fundamental issue. If I look at the limit of just the left-hand side, it's equal to 1. If I look at the limit of just the right-hand side, it's equal to 3. But I want the limit as x approaches 1, which means I need to consider both the left and the right-hand side. And when they don't equal each other, we say the limit does not exist. Yes, the left-hand limit exists as being 1. Yes, the right-hand limit exists as being 3. But no, this combined limit idea where we've got to check both sides does not exist. And then finally, the limit as x approaches 1 of h of x. You can see this one does not have any break in it. There is no hole, but we can still find a value of a continuous function for a limit. Remember, the limit means as we get very, very close to our point of interest. Doesn't have to be an undefined point. So here, if I were to do my limit, the limit as x approaches 1 from the left, I'm looking at 1 here. What's the output I get very close to? H of x is going to be really close to 4. And then the limit as x approaches 1 from the right of h of x. Well, as I go to the right-hand side, I'm getting closer and closer to a y value of 4. So the limit of the entire problem is looking at 4. So that's the graphical perspective on how we look at a limit. We look at the left-hand side, we look at the right-hand side, and we see what are the outputs or what are the y values that we're getting closer and closer to. In the next video, we are going to look at the numerical version of how we determine limits.